Okie dokie, let's go ahead and do a problem. So this is example 1 in the textbook. This is the start of chapter 1.3, and we are going to practice our unit conversion abilities. Now, this is what the example in the textbook asks. This is something I'd like to do extra that'll teach you a little more about why units are so freaking powerful. So let's get into it. And so the question is really cool, and it's talking about the highest waterfall in the world, and it's called Angel Falls. It's in Venezuela. I've never been, but look it up online. It's a beautiful thing. I attempted to draw some water here, but I don't think my camera wants to pick that up. There's my little waterfall picture here, and you can see the trees and the water's coming down, and it's gonna collect into this pool here. But let's say that I'm standing here, okay, and I'm able to know, someone told me that this is 979 meters tall. By the way, I want you to picture that. That's almost a kilometer. Like, that's like the better part of half a mile. That's insane. But notwithstanding the just sheer coolness that a waterfall that's that tall exists in the world, what we want to do is express this height in feet. So let's write this out like we've been doing. And there's no major unit. The unit conversion for this is very easy. So what we say is that this waterfall is 979 meters tall. Now, sometimes you'll have a situation where we just need to convert a unit of length. Like last time in the example I gave you, we converted kilometers an hour to meters per second. So when we only have one unit, it can be tricky to then like do the whole numerator denominator thing. And then you say, okay, you divide, you multiply. If it's been a while for you, it can get confusing. So what I recommend doing to just clear and organize your problem is if it's just 979 meters, add a 1 below it, just so that you know you're still dealing with fractions, and that'll help remind you of what it is that we're actually doing. Let me zoom in a little bit for you guys too. Let me just kind of give you a little, there you go. That's better. Okay, so 979 meters over 1. And, that's the same thing as just saying 979 meters. So we've done the math to start this, and what we know is that 3.28 feet is equal to 1 meter. Now remember our trick here. I'm going to write it down here so we can keep this kind of organized. But 3.28 feet is equal to 1 meter. Let's write that in two ways. So we say that 1, remember, if they're equal to each other and we divide them by each other, then anything that's equal divided by itself is 1, right? 3 divided by 3 is 1. A divided by A, just some random variable A, is equal to 1. 1 divided by 1 is 1. So in this case, 3.28 feet divided by 1 meter is equal to 1. And likewise, 1 meter divided by 3.28 feet, oops, I forgot the unit, is also equal to 1. Now, which of these do we want to use? We have our deck of cards that we've built here, okay? These are in our hand. Which of these do we want to play so that the meter on the top cancels with a meter on the bottom? If we use this one, we're going to end up with meters squared divided by feet, which is, we talked about this. If you do this, a physicist, an engineer, I will look at you with contempt. So we use this one, and we say that 3.28 feet divided by 1 meter is equal to 1. We're multiplying this by 1. The information has not changed, and the meters cancel. So let's go ahead and plug that into our calculator. 979 meters times 3.28 feet. And you know that's right because a meter is about a yard, and a yard is 3 feet. What do you know? There you have it. 3,211 feet. And we just multiplied these two. We said that 1 meter is equal to this many. This is probably something you can do intuitively without the unit analysis, but can you see how it's helpful? So that's nice. Anywho, let's go ahead and tackle the second part of this problem. And this is where units become very useful, because it turns out if we know the height, we actually know a bunch of different stuff. And in this case, it says if I'm falling down at terminal velocity, I'm falling, and terminal velocity is much lower than this, mind you. I just chose a nice number to give us a good, even, kind of, not even, but a good number for our answer. But if I'm falling and I'm somehow going 100 meters per second, which, for record, is like stupidly quick. Actually, hey Siri, 100 meters per second to miles an hour. Yeah. So, you're doing a speedy boy. If I am going that fast, the question is how long until I reach the bottom? So this is where unit analysis is going to become super duper cool. Here's how this works. We start knowing that 979 meters, let's write that here, 979, oops, sorry guys, it appears I've lost my ability to write. We say 979 meters. Remember, we're just going to add that divided by 1. Just clean, easy that way. And what do we have here? We say I'm falling down at a terminal velocity, 100 meters per second. Let's do what we normally do. We're going to write this in two ways. We have 100 meters divided by 1, and we have 1 divided by 100 meters. I don't know what that was. And forgive me, I meant to write 100 meters divided by 1 second, and 1 second divided by 100 meters. I'm sorry, guys, I'm a little tired. The next videos will be better than this, I promise. But we have two of these, and we say that they are not necessarily equivalent. But here's what we're going to do. 100 meters divided by 1 second. 1 second divided by 100 meters. These are the cards in our hand, right? Which one of these will cancel with the meter? And it just so happens to be this one. Let's play it. 1 second divided by 100 meters. And if you already knew this already, there is a formula for this, which you learn very early in mathematics. It's not perfect, but it works. It's called the distance formula. We call it DIRT. Distance equals rate times time. It kind of looks like the word dirt. And if you look here, we've done something very similar to this. We took a distance and we effectively divided by the velocity. We used the reciprocal of it, and that gave us the time. So we actually did DIRT. We did the formula, but we did it by using unit analysis. If that didn't make sense, don't worry. It's just a nice allegory to prove that what we're doing is correct. So let's do this. 979 meters divided by 100 meters. The meters cancel, and what does that leave us with? It leaves us with 9.79 seconds. So unit analysis, just from analyzing the units, we didn't know anything about equations of motion, but just looking at the units, we got to an answer for how long it's going to take to fall. And this is what's really cool, is we use this stuff in modern physics too. Like, if you don't know the equation to something, a good way to reasonably guess, even in like relativity, this was used, is to figure out what units your answer needs to be in, and then work to cancel units using what variables, what information you have. And you end up with stuff like this. So that's really, really useful. Unit analysis is huge, and you can also use it to double check your answers. You know, if I give you a problem where at the end of the day you should get like a distance, and you end up with like distance squared over time, then you know that somewhere you screwed up. And that's a really nice way to double check yourself. So unit analysis is big. That is the takeaway from this example. Hopefully you could convert that just as quickly, probably a little quicker than I could. And in the next video, we will dive into trigonometry, like I said. I just wanted to add this addendum to give you an example of what actual unit analysis does for you and give you a real-life kind of scenario for it. So thanks, guys. I'll see you in the next one. If this was useful to you, follow along in the physics playlist listed below in the description, and leave a like, comment, and do subscribe if you want to stay up to date and learn the foundations of physics. See you guys in the next one. Peace.